Hello and welcome back to this series on graph theory. Today we're going to talk about vertex degree. So for the following, we let G be a graph with vertex set V and edge set E. We further require that both the vertex and the edge sets are non-empty. In what follows, the idea is to look at G locally around a single vertex. So for example, we might have a vertex V in G, and then V could be connected to some other vertices in G. And we look at G locally in the sense that we focus in on a single vertex V and check out what its environment looks like. Our first definition lets us refer to the vertices that are connected directly to V. And we call the vertices connected to V its neighbors. So let V be a vertex in the vertex set big V. Then the set NV is defined as following. These are all the vertices U in the vertex set such that U is adjacent to V. And we call this set NV the neighborhood of V. In our drawing above, the vertices that are connected to V are exactly these vertices I've drawn around V, and these form the neighborhood of V. Naturally, these vertices could be connected to each other or could be connected to other vertices in the graph, but when we're looking at the neighborhood, then we're just isolating all of the vertices that are connected to V. More generally, we can also define the neighborhood of a set. For this, let U be a subset of V. Then the neighborhood of U is the set of neighbors of U in V without U. For example, in this graph I'm drawing here, we could take the yellow points as the set U, and then we would find all of the neighbors of the yellow points that aren't in the set of yellow points itself, which I've indicated in purple. So the purple set would be the neighborhood of the yellow set. To indicate the neighborhood of a set, we use the same notation. So we write n of the set to indicate its neighborhood. An important parameter for a vertex in a graph is the number of edges that are incident to it. We formalize this by defining the degree of a vertex. For this, we let V be an element of the vertex set. We then define the degree of V to be the number of edges incident to V. In the above example, this is exactly the edges I've marked in red. And in the lower example, if we look at the vertex I've marked in red, then we see that it has 2 edges incident to it, so its degree would be 2. To indicate the degree of a vertex, we write d of V. Finally, we call a vertex of degree 0 isolated. Vertex degree is very much a local parameter since it only gives you information about a single vertex of the graph. However, we can turn this local parameter into a global one by looking at the minimum and maximum degrees over an entire graph. For this, we define delta of G to be the minimum over all vertices in the graph of the degree of that vertex, and capital delta of G to be the maximum over all vertices in the graph of their corresponding degree. Small delta is called the minimum degree of G, and capital delta is called the maximum degree of G. The minimum and maximum degrees return the degrees of vertices that are least and most connected in G, but we can also ask how connected is an average vertex. For this, we define the average degree of G to be the sum over all degrees of vertices for every vertex in G, and then we divide by the number of vertices in G. So this is just the usual way we would take an average over any set of numbers, and this is the average degree. We now have introduced these three quantities, and they're related in a very straightforward way. So the minimum degree is less than or equal to the average degree, which is less than or equal to the maximum degree of G. Instead of asking about how many edges are incident to each vertex on average, we can ask how many edges there are per vertex in the graph G. So this gives us another quantity, which we call epsilon of G, which is defined as the cardinality of the edge set divided by the cardinality of the vertex set. In other words, epsilon is how many edges we have per vertex in our graph. Of course, the number of edges that we have in our graph directly influences the degrees of the vertices in our graph. And this fact allows us to relate the number of edges in our graph G and the degrees of the vertices of G. Thus, we have our first proposition, which states that the number of edges in our graph G is equal to 1/2 times the sum over all degrees of vertices in G, and that this is also equal to 1/2 times the average degree times the cardinality of the vertex set. Let's prove this. Note that the second equality follows by definition. Since we've defined the average degree as the sum over all degrees of vertices divided by the cardinality of the vertex set. Thus, we just need to show the first equality, and this follows by counting. What I mean by this is that if we count all the edges in G, then for each edge, E in G, we count its endpoints twice. Thus, each time we count an edge, we count 2 towards the total degree over all the vertices in the graph. Therefore, each edge in G contributes 2 towards the total degree, that's the sum over all the degrees in G. From this, it now follows that the number of edges is half the total degree of G. You should convince yourself that this intuitive argument makes sense. However, in case this didn't click, I'll give a more formal argument. We can prove this same equality by induction. I just noticed that I made a mistake. Actually, we don't need the edge set to be non-empty, we just need the vertex set to be non-empty. Thus, the base case for the induction is where we have a graph that has no edges. And in this case, it follows that the degree of each vertex is 0, which means that this sum is also 0. And in that case, the equality holds. This means that we've established the base case for the induction, and now we do the inductive step and assume that the equality holds as long as the number of edges is strictly less than k. Now we have to show that in the case that the edges equals k, that we also have an equality. For this, we consider our graph G, and we isolate any edge in G. Let's call it E. To reiterate, we assume that the equality holds for all graphs that have less than k edges. And now we take a graph that has k edges, one of them called E, and now we delete E from our graph G and get a graph G prime, which has strictly less than k edges. Thus we get a graph G prime, which has vertex set V, because it still has the same vertices as G, but now it has edge set E without the edge E. And we have that the number of edges of this graph G prime is equal to 1/2 over the sum of all the degrees, and this is the degrees in G prime. Now the quantity we're interested in is the number of edges in G, which is equal to this quantity we know plus 1, since we have one additional edge in G as compared to G prime. And we know that this is 1/2 times the degree, sum of the degrees of the vertices in G prime, plus 1. And now we need to relate the sum of the degrees of vertices in G prime with the sum of the degrees of the vertices in G. So we look at the endpoints of E, which are the only two vertices that are changed in degree by our removal of the edge E, and we see that each of them loses one incident edge when we delete E. Therefore, the sum over all the degrees will go down by 2 in G prime as compared to G. Thus, indeed, this sum over all the degrees in G prime is actually the sum over all the degrees in G minus 2. And now if we multiply out this fraction with the 1/2, the -1 and the 1 cancel, and we get the desired equality. Notice that this more elaborate inductive argument uses exactly the same principle as we appealed to in the intuitive counting argument, namely that each edge increases the total sum of the vertex degrees by 2. Despite being fairly simple, this equality here that relates the number of edges with the sum over all the degrees in a graph is very useful, so it's worth remembering. Finally, note that by dividing this outer equality by the cardinality of V, we get that the epsilon of G is actually 1/2 times the average degree of G. I'll conclude today with the following riddle. It asks whether it's possible for everyone in a group of 9 people to shake hands with exactly 3 other people in that group. We can model the situation by representing each of the people as a vertex in a graph. And then we could draw an edge between any 2 of the vertices that have shaken hands. So for example, we could have 1 shaking the hand of 9 and vice versa, maybe also 1 and 8 and 1 and 7. And now 1 has maxed out on how many people he's allowed to shake hands with. We can continue. We know that 9 still has 2 other people she needs to shake hands with. For example, 2 and 3. And then for 8, we can do the same thing. For 7, now 2 has the maximum amount of edges that it's allowed to have incident to it. 7 and 3, maybe. And now we see that we have a problem, namely that there are no people left for 6 to shake hands with. Thus 7, 8, 9, 1, 2, and 3 have all shaken hands with exactly 3 people. However, there's no third person available for 6 to shake hands with. We might think that we've just made a poor choice in the way we've drawn edges, but if you play around with the situation, you'll find that in fact it doesn't seem possible to draw the edges in such a way that we would get a graph on 9 vertices where each vertex has degree 3. In fact, this is the final proposition we'll prove today. It states that the number of odd degree vertices in a graph is always even. Thus, in particular, if we have a 9-vertex graph, we can't have all of those 9 vertices having an odd degree, for example, 3. The proof uses the degree sum formula we proved before. We have that the number of edges is equal to 1/2 over the sum of all the degrees in our graph. However, we also know that the number of edges has to be an integer. So we can't have half an edge, for example. This implies that the second quantity, the sum over all the degrees in our graph, has to be an even number. We can split the sum over all the degrees into the sum over those degrees that are even and those that are odd. Now this first quantity here will always be even, since summing over even numbers always gives back an even number. From the above equation, we know that the total sum also has to be even, which now implies that the sum over all the odd degrees also needs to be even. Otherwise, summing an even number and an odd number would give an odd number, and we need the total sum to be an even number. Now, the only way for the sum of odd numbers to be even is if we have an even number of terms in that sum. Therefore, our considerations on the parity of this sum implies that the number of odd vertices is in fact even. And this concludes the proof. With this proposition, we can now give a definitive answer to our riddle, which is that no, it's not possible for everyone in a group of 9 people to shake hands with exactly 3 others. This concludes what I wanted to say about vertex degree. Next time we'll be looking at paths and cycles in graphs.